All right, so section 2.6. So going into chapter 2, and we're going to talk about piecewise defined functions. And piecewise defined functions means it's we're calling it one function, but it's several pieces, 2, sometimes 3, sometimes more pieces that we're building that one function from. So piecewise defined functions are functions that have multiple parts. And those parts are defined by specific domains. And remember, domain are x values. Okay. Domains x values, ranges y values, and the domain is going to be, we're going to find the domain of some of our piecewise defined functions. We're also going to talk about the range. The range, remember, is your y values, the up and down out of that. So the graph is really helpful in finding the range. The domain, the great thing about it is they give it to us in the piecewise defined function. So we don't have to search for it. We don't have to do a lot of calculating to find it. We don't have to even think about those red flags that we talked about in 100 to do that. So domain, they're going to give you, and you just got to kind of interpret it. And then the range, the graph is really helpful in finding that. So let's just start off with an example here, something fairly simple as far as the pieces are not overly complex equations. So example A, our first piecewise defined function, and I use a big curly brace to say these pieces make up this function. So negative 3x plus 4 if x is less than or equal to negative 1. And then the second piece is x plus 5 if x is greater than negative 1. Okay. So they give us this piecewise defined function. It's piecewise because we have multiple pieces defined by these domains. That the first part works when x is less than or equal to negative 1. Okay, so all the x's on the first part are from negative infinity up to negative 1, including negative 1. The second part is used for all the x's that start at negative 1, but we don't include it and go to positive infinity. So it's x's that are greater than negative 1. So those are the pieces, and that's the definement. The defined is the domain. That's what defines where that's happening at. So once we start drawing the pictures of this, I think it starts making a little bit more sense. So let's start by just graphing these, and I'm going to show you how to go about graphing it and what's important when you are graphing piecewise defined functions. So I'm just drawing on a little coordinate plane here. And when you're doing piecewise defined functions, you got to remember that these domains over here are the x values. So this is an x value that's important for that part. Negative 1 is an important x value for negative 3x plus 4. So I need to find out what y value goes with that. So there are important points. One of those is at negative 1, and then we got to find the y value that goes with it. So we're going to plug in negative 1 into this first piece, and I'm gonna put a blue dot beside that. So everything I do in blue is related to that first piece. Okay, so 3 times negative 1, and then add 4. That would be positive 3 plus 4 is 7, right? So the ordered pair that's important is negative 1, 7. Okay? For that piece, that's an important point. And it is a closed dot because it has an equal to mark on the inequality. It's got that line underneath it. So that means I'm going to go to negative 1 and then 7. 1, 2, 3, 4, 5, 6, 7. There, I'm going to put a closed dot. If it doesn't have the equal to mark, I'd put an empty circle there, just showing where it's at, but an empty circle. So it would look something like that. if it wasn't an equal to mark. And now I need to get the rest of the picture for that first piece. So negative 3x plus 4, well, that's a linear equation. So there's a couple of different ways I can get the picture. One of those is to think about the slope. And the slope is negative 3 in this case. So that means I'd go down 3 and right 1. But if I go to the right, I'm getting past the x values they told me worked. So I've got to go the other direction. So to do a negative 3 slope to the left, I got to go up 3, left 1, up 3, left 1. I could do that on and on. And I get this line going like that. It's a straight line because it's in slope-intercept form. Y equals mx plus b, negative 3x plus 4. But it doesn't get to the plus 4 because it's, that would be where x is 0, and that stops before it gets there. Another way to get those points out here to the left would be to just pick x values that are less than negative 1. If I pick negative 2 for x and plug that in, that would be 6 plus 4 is 10. That's that point right there. That's 16. And if I pick negative 3 for x and plug that in, that'd be 9 plus 4 is 13. That's that point right there. So you can get the picture by picking x values or by using that slope to help you. I like using the slope just because that's quicker than plugging in points. And it's a linear one, so I know that about it. All right, the next thing we'll do is working on the second piece. So we've got the picture for the first piece. The second piece, the important x value is also negative 1. It won't always be the same number. A lot of times it is, though. So it won't always be the same number, but most of the time it is. Okay, so I'm going to pick negative 1 for x, and I'm going to plug it into this second piece so that I can find out what's going on there. Negative 1 plus 5 would be 4. So at negative 1, positive 4, 1, 2, 3, 4, I'm going to put an open circle because that inequality doesn't have the equal to mark right there. So it's an open circle because it doesn't have the equal to mark. And then I'm going to graph that for all the x's that are greater than negative 1. So that means I'm going to the right of that. And the slope is up 1 over 1 because there's a 1 in front of x there. And that means it goes this way. I could also pick x values that are bigger than negative 1 and plug them in. 0 plus 5 is 5. That's that point right there. 1 plus 5 is 6. That's that point. 2 plus 5 is 7. That's that point. I could keep going there. Okay. Once I see the picture, that helps me to talk about the domain and the range. Okay. Domain. Let's do that in first. Domain, they give us up here. All that stuff up there is the domain. They say all the x's that are less than negative 1 and including negative 1. And then the second half says, okay, don't include negative 1 in this part, but go everything up to positive infinity. So the domain for this one doesn't leave anything out because negative 1 was used in the top half. The second half left it out, but it was already used once. So once it's used, it's used. So you're not throwing it out. So the domain for this one is from negative infinity to positive infinity because all the numbers are accounted for. If this first one did not have the equal to mark, then you'd have an x doesn't equal negative 1. You'd have to just throw out the negative 1. But since it does have the equal to mark, it picked it up, so we don't have to throw it out. The range, this is where the graph comes in. The range, you read from bottom to top. Domain, you read from left to right. Domain and range, you read from bottom to top. So when I'm reading this from bottom to top, the lowest point that I know about is right here. And what's the y value for that open circle right there? It's 4. So my range is going to start at 4, and then this red one goes up, keeps going up, right? That arrow at the end tells it just keeps going up. The blue one also keeps going up. So that's going toward positive infinity for the range. So that's going to be from 4 to positive infinity for the range. Another way to write the domain for this one would be x such as all real numbers. That would be the set notation. Remember doing that in 100. For this one, for the range, you could write it y, as long as y is greater than 4. Those would be the set notations for the range and the domain for that. Okay. One other thing that we want to talk about here, and then we'll go and graph this on the calculator, is a thing called continuous or discontinuous. It's called continuity is what the topic is. If something is continuous, what does that mean? If something doesn't necessarily have to be mathematical, is continuous, what does that mean? It does. Keeps going forever, right? Never stops, never takes a break, right? If it's discontinuous, the prefix dis, dis means the opposite of that, right? Not continuous. All right. So for this particular graph, does it take a break? Is there a spot there where you have to take you have to jump to get to the next piece? Well, if I trace this blue and, I'm going to take a highlighter and trace it. At that spot, I've got to pick the highlighter up and jump to this spot to start tracing the other spot, right? And because I had to pick my pencil up to trace it, that would be a reason to call this one discontinuous, because it has a break in it. Okay. Anytime it has a break in it, that's going to be discontinuous. Kind of the layman's way of defining continuous and discontinuous is discontinuous, you have to, if you trace the graph, you've got to pick up your pencil to move. That's discontinuous. If you can trace it and not have to pick up your pencil, it's continuous. Okay, so really easy idea. It's just basically looking at it and seeing, okay, can I trace that without picking up my pencil? If I can, it's continuous. If I can't and I have to pick up my pencil, it's discontinuous. So let's look at graphing this with the calculator. I'll show you the way that it's done. I don't generally graph a lot of these with the calculator. Just because it's a lot of button pushing, but it does work, and it does give you an idea whether or not you graphed it correctly, for sure. So let's look at that. So graphing calculator, I'm going to hit the Y equals button, and I'm going to clear out this stuff that I had in here from earlier today. Okay, so with piecewise defined functions, I can't graph all of the pieces on one single y equals. I've got to use how many pieces I've got to use that many y equals spots. So I'm on one part per y. So for y1, I'm going to do the first part, and I'm going to put it in parentheses. This is important that you put the equation part, negative 3x plus 4, in parentheses like that. Okay. You've got to have it in parentheses so that we can do the piecewise part, the inequality part. If we don't have that, we're in trouble. All right. Then we hit the division symbol and then open up another set of parentheses. And this is where the inequality part goes. It goes in this set of parentheses. And this one says that x is less than or equal to -1. So I'm going to type that in. X, and then to get the less than or equal to symbol, I've got to hit second, the math button. Second and math takes you to this test menu. And it's got the inequality symbols in there. We just need to pick the one we want. We want less than or equal to, and that's the last option. That's number 6 there. Less than or equal to, and then I type a -1. Close those parentheses, and I'm going to hit graph just to show you that picture of that part of the graph. That is that line that we drew by hand right here. Right? It's right up there. Go to the graph. It's right up there. We see that piece out of that. Then I'm going to hit y equals. I'm going to go to y2, and I'm going to put the second piece in there. So parentheses, and then x plus 5, close the parentheses, and then division symbol, and then open up a set of parentheses. And I want to do x is greater than -1. So x, and then second math, greater than is the third option there, -1. Close the parentheses, hit graph. There's the other piece that we drew on our graph by hand. The only thing that's hard to see here is the open circles and filled in circles. It doesn't put those there. Okay, that's the drawback to drawing it on the calculator. But it does give you an idea. Hey, did I get the right picture out of this? Is this the right one for that particular graph? And it can help you find the range by just looking at that picture on the graph like that. Okay, so we're going to kind of try to do some of that as we go here with this particular stuff. All right, let's look at another example and see if we can go through those steps with it. It's got some different pieces to it. So get a little bit of review of some of the family of functions that we talked about in 100 with all the different graphs as we go through here. So absolute value of x if -3 is less than x is less than 2. No equal to mark there. Sorry, messed up on my drawing. X squared plus 3 if x is greater than or equal to 2. So put the equal to mark on the second one. All right, so no equal to marks on the first piece, but an equal to mark on the second piece. All right, so we've got to look at that and decide, okay, where are the important places on these graphs? So the first piece, we'll do, again, I'll do everything in blue for the first piece. It has an inequality that has two numbers on it. It has a -3 on the lower end and a +2 on the upper end. So that means it's going to have two important points. It's going to have a point at -3, and then plug that in. What's the absolute value of -3? It's 3. So at 3, 3. And then it's going to have one at 2, and then you do absolute value of 2 is 2. At 2, 2. All right? So those are important points for this particular graph. So I'm going to draw myself a little coordinate plane here. I know I've got to have some room up top because I know something about the second one. I'm just going to make it look like that. And I'm going to put an open circle at -3, 3, and an open circle at 2, 2. Because neither of those have an equal to mark. So that's why they're open circles. Okay. Now I need to find out what's going on in between there. So I need a few points. What do I know the shape of the absolute value graph is? Anybody remember? The V shape. Yeah, it's a V. In that particular equation, the V would be at the corner would be at 0, 0. If I plugged in 0 for x, the absolute value of 0 is 0, right? So I know that point works. And then I could plug in -1. -1, the absolute value is 1. -2. I could do that and get those points in between and see that I get that V shape happening for that little space right there. Okay. So there we have our first piece. Let's get the second piece. We know that that's an x squared graph, so we know that that looks something like this normally. U-shaped graph, that parabola shape. And I know it's an important point at 2. So I'm going to plug in a 2. 2 squared plus 3. So that'd be 4 plus 3 is 7. So at 2, 7, I'm going to put a point. 2, 3, 4, 5, 6, 7. All right. And then take that, and I need all the x's that are greater than that. So I just need to get a few that are to the right of that. So I just need to plug in some x values that are bigger than 2. So if I plug in a 3, 3 squared plus 3, that's 12. So I go 8, 9, 10, 11, 12. That's getting me up into that. But I know it's going to be this parabola shape, so it's going to go up and to the right. So I get that kind of shape happening for me. All right. Now, domain and range of this one. Okay. So domain. They tell me right here what's going on with the domain. Those things tell me what's up. They say it starts at -3, but it doesn't include -3. So that's going to be -3 with a parenthesis beside of it. And then that first piece goes up to 2, but it doesn't include the 2. So then I jump to the second piece. It picks up the 2 and uses it. It says, okay, you don't want the 2? I do. I'm going to use it. So we're not skipping 2. We're going to use 2 and everything bigger than that. So that gets us toward what? Positive infinity. So from -3 to positive infinity are going to be our x values that are used for this. It can also be written x as long as x is greater than -3. That would be the set notation for that. Both of those mean the same thing. Okay. The range, this is where the graph comes in handy. Remember, range will read bottom to top. So start at the bottom, find the lowest y value. Well, when I find the lowest y value, it's right here. It's at the origin. It's at 0. So I'm going to start at 0 and go up. Well, if I go up, hey, it stops right here at this spot at +3. And it's got an open circle on it. And then it skips a bunch of y values until it gets up here. And it not only does it get up to here, that's a 7, and it's got a closed circle on it, so it's included, so it's a bracket. And then that red line just keeps going up forever. So that's what's going to get us on the positive infinity there. Now the set notation for this, not quite as nice. Y is 3, or let's do this. 0 is less than or equal to y is less than 3, and y is greater than or equal to 7. That would be the set notation for that. Set notation is not quite as nice on that range because of the skipped spot of that. Is that a continuous or discontinuous graph? Can I trace it without picking up my pencil? No, I got to pick up my pencil to get to this next piece. So that's going to be discontinuous. Discontinuous. It's got a C in it, doesn't it? So domain, range, discontinuous. Let's look at the calculator way of graphing that problem, and then we'll maybe move on to the next one there. So I'm going to go to y equals. I'm going to clear out these others that I had, and I'm going to get the absolute value of x in the first place. I'm going to put it in parentheses no matter what, okay? Now, to get the absolute value, your calculator has that in the works. You got to hit the math menu, then press over to number, because that's what you take the absolute value of, is numbers. And that first option is ABS. And it should either give you the sticks, or if it puts ABS parentheses, that means the exact same thing. Okay. So to get that, again, parentheses, and then hit math, the right arrow key, and that first option is ABS. That's the one you want. Mine is set to use the sticks for absolute value. Yours may be set to say ABS parentheses. They mean the same thing. It doesn't change how it works. Now I'm going to put the X in there. And then if yours says ABS parentheses, you're going to close those parentheses. I'm going to press the right arrow key and then close the parentheses for that. And then divide. And then now I got to put the inequalities in there. This one's a little tougher because my inequalities have I've got two things going on here. I've got two things. I've got x is greater than -3 and x is less than 2. It's x is greater than -3 because of this n down here is that. It's like read it backwards. Notice how it's pointing toward the -3. It's still pointing toward the -3 there. And then that is, the calculator doesn't have enough coding in it or brains in it to understand this compound inequality. You got to split it into two inequalities. So that's the reason I'm having to do that. Okay, it can't handle the compound inequality. So I'm gonna put parentheses after the division symbol, parentheses, and I've got to type in those two inequalities. I've got x second math is greater than -3. And then I've got to use the word and. So the calculator, to get that, you got to hit second math, go over to logic, and is the first option. And then I type in the second inequality. X, second math, is less than 2. So 5, 2, close parentheses. If I hit graph, I should see just that small portion of the V. Math, okay? Kind of see why I don't do a lot of these with the calculator. I'm quicker at it by hand because usually it's not a really big graph anyway. And then let's go to the second piece, parentheses, x squared plus 3. Close the parentheses, division symbol. And this is x is greater than or equal to 2. So x, second math, greater than or equal to 2. Graph. And I'm only going to see a small portion of that, just like I only saw a small portion of it. If I scroll down here, I only see a small portion of it in my hand-drawn picture too. But I get the idea of what's going on with the graph. If I wanted to zoom out and see a little bit more of that curve, I could, but there's really not any use in that for this problem. Okay, so calculator can be helpful. Just got to know what to tell it to do. Not exactly the easiest thing to tell it to do is graphing piecewise, but it just takes some practice. Let's do another one and finish up. Just make sure we got this down, and then we'll get into the other thing about piecewise defined functions in this section. Let's do one that's got 3 pieces to it. They don't usually get much bigger than that, so I want to make sure I do one that's got at least 3 pieces in it. So the first piece is going to be, the graph looks like -2x if x is less than -3. And then it looks like 3x minus 1 if the x's are from -3 to +2, including both of those. Okay, so we're using the -3 in the second piece, not in the first piece. Okay, we're using the 2 in the second piece. And then this last piece, let's do -4x if x is greater than 2. Okay, so 3 linear pieces in there, nothing fancy going on as far as the pieces go, but it's got 3 pieces, so it's got to be a little bit more difficult. So first thing that I would do is just start with the coordinate plane and get my start with that first piece and get the important point for it. So the first piece, the x value that is important is -3. So when I plug -3 into this first piece, that's going to be -3 times -2, which is +6. So it has, and I'm going to graph it in blue. The first piece is all in blue. That'd be -3, +6. So I'm going to go to -3, 1, 2, 3, 4, 5, 6. And then I'm not going to put a filled in dot. I'm going to put an open circle because it doesn't have an equal to mark. Okay. And then I need to find out what's going on for x's that are less than -3. So that's to the left. So if I plug in a -4, -4 is to the left. -4 times -2 is +8. So that's going to be this point. And then I can plug in a -5. That'd be +10. Be that point. So that piece is going to be a straight line going that direction. We know it's linear because the x didn't have any exponents on it. All right, so that's how we know that that's going on. All right, let's go to the middle piece, and I'll do it in red. It's got two important points, one at -3. So I plug that into x. So -3 in here for x. 3 times -3 is -9. -1 is -10. And then the other important point is at 2. So I take this 2 and I'm going to plug it in for x right there. 3 times 2 is 6. -1 is 5. Both of those have equal to marks, so they're going to be filled in dots. All right, so I'm going to go to -3, -10. Filled in dot. And then I'm going to go to 2, 5. That's right, yeah, 2, 5. And put a filled in dot. I know that that's a straight line because the x doesn't have any variables or any exponents on it. So I'm just going to connect those two dots. I don't even have to do anything in between because I know it's a straight line. The next piece, I'm going to do in green. It should have an important point at 2. Plug that 2 into this. -4 times 2 is -8. I'm going to go to 2, -8. Right there. And that should be an open circle because it doesn't have an equal to mark. And then what's going on past the 2? Oh, if I plug in a 3, it's going to be -12. Down 4, over 1. Down 4, over 1. So we get this picture. All right, so definitely, is this continuous or discontinuous? Can I get from the blue part to the red part without picking up my pencil? No, I gotta jump from this spot to the next spot to get to. So to be discontinuous there. Discontinuous is the most common one. I think every one of them we've done has been discontinuous. That's very common because you're dealing with piecewise. They're going to be pieces, and they don't always end to end match up there. So this will be a discontinuous one. Let's get the domain. And we can get the domain straight from this stuff. We start at -3. Excuse me, we use -3 in the second piece. Right there. Right? Or back up. First one is x is less than -3. So that's going to start at -infinity, isn't it? And it's going to go up to 3. And then the first piece doesn't use it, but the second piece does. And then it uses all of them up to 2. But then the last one doesn't use the 2, but that one did. So the 2 is used, and everything above 2 is used. Hey, what do you know? The domain is going to be -infinity to +infinity. Even though they broke it up into 3 pieces, every number was used out of there. So that's why we don't have any spots that are skipped out. That's nice. The range not going to be quite as nice, but it's not bad. If we read bottom to top, so the green one is the lowest one, and it's going toward -infinity. So that's where we're starting. And it goes up until I get to right here, but then the red one picks up and goes all the way up to that spot right there, which that y value was a 5. So we use a 5. and it's a filled-in dot, so that's going to be a 5 bracket. But we skip the y values from there until we get to there. So that's going to be a union, and then the parentheses, this y value was a 6. Remember from the blue spot, the 6, that's that y value right there. So we're going to put a parentheses, 6, and then this one goes up to infinity. That's the domain. And you said this one was discontinuous. Now that's not the funnest thing in the world. It's tedious. There's a lot of things to look at, a lot of things to get pieces of, but it's piecewise, and they're not going to be just incredibly hard. Each piece individually is not an incredibly hard piece. So don't get overwhelmed in thinking about all three of them together. Think about one piece at a time. It's kind of like the old saying, how do you eat an elephant? One piece at a time, or one bite at a time. These piecewise defined functions, if you'll just focus on one part at a time, they're doable. Don't feel like you're overwhelmed with those. All right, the last thing for this particular section is the easiest thing in this section. Is function value. And function value with piecewise defined functions. Y'all remember doing function value? We'll do a review problem first. So let's say we had f of x is equal to 3x squared minus 7. And they said find f of 2. That was function value. So this will be example D. Find f of 2. What did that mean we did with the 2? We put it where? In the place of x. Everywhere there's an x in the problem, we put that 2 in there. Okay? And it was easy because there was only one piece to look at. It was the 3x minus 7, or 3x squared minus 7. We didn't have to look for anything else. So we just worked that out, and we got 3 times 2 squared. Order of operations says you got to square 2 first, which is 4. 4 times 3, and then subtract 7. So that'd be 12 minus 7, which is 5. So we would get f of 2 is equal to 5. That was our final answer when we did function value out of that. So that's what we're doing. We're going to use a piecewise defined function to do that. All right. So let's look at a piecewise defined function and try to do some function value with that. Not that much more difficult, but it is different because it's piecewise defined. So piecewise defined function. Let's just get us a function here. Let's say x to the third power plus 2x squared minus 5. A little bit more complicated, but we're not having to graph this. All we're doing is finding function value, so it's not a big deal. And then the inequality that goes with that is if x is less than negative 6. And then let's use 5x minus 8 if x is greater than or equal to negative 6. Okay? So just a two-piece, piecewise defined function, and negative 6 seems to be the breaking point in between the two domains. So what we're going to do is we're going to take this and we're going to find function value. And let's say they ask us to find f of positive 10. The key to this is to look at that number and decide which piece does it go into. And the way you decide is using these inequalities out here. Positive 10 is positive 10 less than negative 6. Positive 10 less than negative 6. No, definitely not. Is positive 10 greater than or equal to negative 6? It's greater than that, right? So that tells me that, hey, this positive 10 fits that inequality. So that means when I plug this in, I'm going to do 5 times 10 minus 8 because it fits that inequality. I don't use the other one because it's not less than negative 6. Okay? And then I just work that out. f of 10. 5 times 10 is 50 minus 8, so that'd be 42. Final answer of 42 on that. We use the same piecewise defined function and are asked to find f of, let's say, -9. Well, if I do that, -9 is -9 less than -6. If I owe you $9, is that worse than owing you $6? Yeah, it is. So that'd be -9 means I owe you more money. So that is less than -6. So that means that this problem, I'm going to use the first piece and plug that in there. I'm going to use the calculator to help me here because I don't know my -9 to the third power. So I'm plugging in -9 into this problem. So parentheses -9 raised to the third power, and then plus 2 parentheses -9 squared, and then is it plus 5 or minus 5? Minus 5. Minus 5. And enter. -572. Little calculator magic there. That's wonderful. But that's all we're looking for is what is the y value when that goes. We just got to find which piece does it go into. Which one do I use? So you have to check your x value with those inequalities. And if it will fit in one of them. Okay, if it doesn't fit in one of those, maybe you've written the problem down or something wrong uh, out of that. So you've got to find which inequality does it fit in. Whichever one it fits in, you use that piece to evaluate your function. Okay, so function value with piecewise, easiest thing we've done so far tonight, so far in the course. There are some, it doesn't get any harder than that. Really, it is that easy. Okay. All right, so there is section 1, or the first section of the night. We got a couple more to go here. and we'll just trudge on into the next one here. I'm just going to use regular paper for this one. We're not going to be graphing anything on this one. We're just going to talk about function operations and compositions, and then deal with domains and ranges of those, which is a fun thing. I use fun in a very loose sense of the word. So, section 2.8. So it's at least in the same chapter. So it's going to be semi-related to what we're doing so far. So we're talking about function operations and compositions. All right. All right. When we're doing function operations and compositions, we deal with the domain with these. We don't worry so much about the range. We're just going to talk about domain mainly in this section. So when we talk about domain, so let's just get a quick refresher on domain of a regular function. These are not going to be all piecewise defined functions. There are a few that crop up in this section, but not very many. But the things that we looked at in Math 100 about domain. And so the red flags that we talked about in 100, red flags for domain. One of those red flags was division by 0, or division with variables. Remember, if you had an x in the denominator of the problem, you had to do some stuff to work that out. The other red flag that we dealt with were square roots. So those things still occur when we talk about function operations and domains that are related to those. So when we're finding the domain of a function operation, we're still looking at the same red flags that we did with just one function out of that. So let's review that just a little bit a couple of equations here, and just find the domain. So example A is just one function. F of x is the square root of 2x minus, let's do 9. 2x minus 9. So we're going to find the domain. So that one obviously has a square root symbol in it, and if it's got a square root symbol in it, that's a red flag because it has the x underneath it. So what we did with that in 100 was we took the stuff that's underneath the square root. Anything else that's in the problem, if there were a +6 out here and maybe a 4 out here, those would have absolutely nothing to do with finding the domain. You only take the stuff that is underneath the square root, and you take it and you set it greater than or equal to 0 to find the domain. So we're kind of going back to doing that a little bit in this section. So we're setting 2x minus 9 greater than or equal to 0, and we're just going to solve that for x. I'm going to add 9, and then last step would be divide by 2. We get this fraction, x is got to be greater than or equal to 9 over 2. And, set notation, that's what it looks like. Interval notation, it would be bracket 9 over 2 to infinity. That would be the way the domain can be expressed for that particular problem. Okay, so square root in the problem, we got to do the greater than or equal to 0 stuff. Review one of the others. So we had g of x is equal to x to the third power over x minus 9. Something like that. This one, the red flag that exists is the x minus 9 in the denominator. That's the problem. We can't have division by 0, so we've got to set up when does the denominator equal 0? When does x minus 9 equal 0? So we just set up whatever's in the denominator, set it equal to 0. So we add 9, and that would be x is equal to 9. When x is equal to 9, then that's when we have the problem. So that means x cannot be 9. So that's what your set notation would look like. Interval notation, I'm going to use a different color. I don't orange, you can't hardly see. All right. I struggle seeing it. All right. And then, so with interval notation, we're going to go from negative infinity up to 9, union 9 to positive infinity. Those would be the domain of that particular function. What we're going to be doing in this section is doing some operations and then finding the domain of that answer that we get. So we got to be able to do these sort of things with two functions that we're putting together. Now, if neither of those red flags exist, the default domain is negative infinity to positive infinity, or all real numbers. And so if there's not any restrictions, then you get that easy way out there, and that happens some with this. So we're going to look at some function operations real quick, and then get into the compositions, which is a little bit more difficult. So function operations. So I'm going to give you two functions. We're going to use the same two for several operations here. So let's do f of x is x squared plus 5x minus 3, and then g of x is negative 3x plus 4. So pretty simple equations there. Nothing just crazy. We know already that the first one, f of x, there are no red flags. There's not a square root. There's no fraction in the problem. So there's no red flags on that one. So that means, hey, that one doesn't have any restrictions on the domain. Look at g of x, and it doesn't have any either. So that's promising in the fact that when I do an operation, I don't have anything kind of underlying to look out for. So being able to recognize the domain of the original functions is very helpful in finding the domains of the others. Okay, so let's look at addition first. So the way the notation works for function operations is they'll say f plus g of x. What that means is you're going to take f of x and add g of x to it. All right. So I'm going to take x squared plus 5x minus 3, and I'm going to add negative 3x plus 4, exactly like it says. When I add two polynomials together, I'm trying to just put like terms together. That's all I'm doing. Okay. So I want them in descending order at the end. So x squared, there's nothing else like it. So I'm going to put it in down. 5x plus negative 3x would be 2x. Negative 3 plus 4 would be plus 1. And there I have found the function, the sum of the two functions, I guess is the best way to say that. Now, if I'm asked for the domain of that, I look for red flags. Are there any red flags in that answer? No, there are no square roots. There's not even a fraction. So there can't be any division by x because there's no division in the problem. So the domain is going to be from negative infinity to positive infinity out of that, because there were no red flags. If there are red flags, then we got to take care of that. There's not any in this one. Okay. Let's take the same two functions, those same two up there, and let's do f minus g of x. Let's do the subtraction. So we're going to take f of x and subtract whatever g of x is. So f of x is x squared plus 5x minus 3, and I'm subtracting negative 3x plus 4. Okay. So I'm just taking those same two functions that are up here. Notice I put them in parentheses this time because the subtraction sign is going to kind of, it'll mess us up if we don't. Okay. So when I subtract, I'm again doing like terms, same rules. X squared minus, there are no other x squared, so that's just going to be x squared. Positive 5x minus negative 3x. That's a double negative. So that's going to be negative 5 plus 3, positive 5 plus 3, which is positive 8x. Then I have negative 3 minus positive 4, so that's going to be negative 7. That is the difference of the two functions of subtraction. Are there any red flags as far as that function goes? No. So the domain is from negative infinity to positive infinity because there are no red flags. A general rule about domains for addition, subtraction, and multiplication of two functions is that the domains will just combine. So if there are red flags to one of the pieces, it's going to be a red flag to that operation of addition, subtraction, and multiplication. Okay, so let's get a couple of different functions. Let's say f of x is 3x plus 5, and g of x is x minus 7, something like that. It's simple stuff here. And the function operation we want to do looks like this: f g of x. That means f of x times g of x. This is multiplication. Okay, we're multiplying two functions together. All right, 3x plus 5. I'm going to use parentheses and then x minus 7. We did this in 100. It's just straight, it's distributed property twice. 3x times x, 3x squared, 3x times negative 7, negative 21x. Then multiply everything by the 5. 5 times x, positive 5x. 5 times negative 7, negative 35. And then simplify that. 3x squared minus the 16x and minus 35. That is the multiplication of those two functions. The domain, negative infinity, positive infinity. Whatever the domains are of the original functions, for the domain of the addition, subtraction, or multiplication of those functions, you're just going to combine them together. So if they're both already negative infinity to positive infinity, when you combine that together, it's still going to be negative infinity to positive infinity. If one of them had a restriction, then you would have a restriction on your operation out of that. We'll see that in just a little bit. We'll do some examples of that. Now, that holds true for addition, subtraction, and multiplication. When you throw division in there, you're creating an exception or a restriction out of that because you're automatically putting an x in the denominator because you're doing division. Okay, so let's do division of these two and look at that domain. F divided by g of x. That means take f of x, divide it by g of x. We're not going to do the log division for that. We're just going to do, set it up there, 3x plus 5 over x minus 7. If there was something obvious that I could cancel out, like everything's divisible by 4, I'd divide them all by 4. But there's not in this case. So that's it. That's the answer to the operation. Now, the domain for that, what's the red flag that we've created? We've created a red flag of an x in the bottom. So we've got to take care of that. We've got to say x minus 7. When is it equal to 0? When x is equal to 7. So that means x can't be 7. So our domain is from negative infinity up to 7, and then from 7 to positive infinity. Or in set notation, x does not equal 7. Both of those are the same thing for the domain there. Interval notation, set notation. All right. So addition, subtraction, multiplication, the domains kind of just they combine together. The division, they're not going to. Okay. You're going to create something new with your domain out of that. So what do you do if you've got some things that are already have restrictions on them? So like your original functions that you're supposed to be putting together have some restrictions on them. So let's look at that. Let's say we had two functions. Let's say f of x is the square root of 2x minus 1 plus 5. That's f of x. G of x is just 8x minus 9. Just that, 8x minus 9. And they ask us to find f plus g of x and the domain. So they're saying find this and state the domain of that. So we're going to take those two functions and we're going to add them together. So f plus g of x. Let's take the function, add them together. So square root of 2x minus 1, and the plus 5's on the outside, plus 8x minus 9. So that square root stuff, it can't combine with anything else because nothing else is underneath the square root. So it's just going to be part of the answer. And then we got a like term right there. We got 5 and negative 9. They could go together. So I'm going to put plus 8x and then minus 4. It's 5 minus 9 is -4. And there would be my addition of those two functions. Now, the domain of that, where does the restriction come from on the domain? What do we have to take care of? The 2x minus 1 there, right? That part, the part that's underneath the square root, that's where the restriction in the domain is. If we look at our original functions, that already existed up here, right? So what we're doing is we're finding the restriction on the addition, but it's really just one of the restrictions from the original ones. Okay, so it's combining with the other equation and its restriction. So we're taking 2x minus 1, and we're supposed to set it greater than or equal to 0 because that's what you do when it's a square root function. Okay, and then work that out. So solving this, plus 1, 2x is greater than or equal to 1, divide by 2, x has got to be greater than or equal to a half. So our domain, x has got to be greater than or equal to 1/2. 1/2 to infinity is the interval notation for that. Okay, so that restriction on that f of x function kind of took over, and it becomes the restriction over the addition. It would do the same thing for subtraction. It would also do the same thing for multiplication. That one restriction would take over for the whole thing. So if there's it's kind of like the saying, chain's only as strong as its weakest link. The link in that chain, if it's one weak, it's going to cause a problem. The same thing happens with the functions. If one of them has a restriction, then everybody's going to have that same thing going on when you're doing addition, subtraction, or multiplication. Okay. When you do division, it creates a whole new thing. So let's look at division for these same two functions. Again, f of x, I'll rewrite them here. F of x is equal to, square root of 2x minus 1, excuse me, plus 5, and then g of x was 8x minus 9. And let's do find f divided by g of x and domain. All right. So pretty easy to set up here. So you're just taking the f of x function and taking square root of 2x minus 1 plus 5 on the top, and the g of x function, 8x minus 9 on the bottom. Okay. Domain, though, there's nothing we can do to simplify this. It's not going to get any prettier as far as the function goes. So that's the function. That's the answer. The divisions are always easy because there's really not much you can do. Okay. Now, the next thing is to find that domain. And there's a couple of different red flags in this one. One of them is that one we just saw in the last example. You got the square root thing going on there. So we know that piece right there tells us that x has got to be greater than or equal to 1/2. But this piece tells us something that x can't be, right? Because we're going to take 8x minus 9 and set it equal to 0. Plus 9, plus 9. 8x is equal to 9 divided by 8. X cannot be 9 over 8. Is 9 over 8 bigger than 1/2? Yeah, it's 1 1/8. 1 1/8 is definitely bigger than 1/2. So there's a number that is in this, the red part, that we got to skip over. So our domain in set notation be x is greater than or equal to 1/2, and then x does not equal 9 over 8. That's on that edge there. I'm going to write 9 over 8. All right? So there's the set notation. The interval notation, bracket 1/2 to 9 over 8, parenthesis, union, parenthesis, 9 over 8 to infinity. Not too bad on the interval out of that. But again, it's created a new restriction there. Division is always going to create a new restriction. The others are just going to combine any restrictions that you have out of that. So addition, subtraction, multiplication, definitely easier to find the domain. You just mash it all together. Division, you're always going to create a new one. The next, let's look at taking function value with operations. And this is not terribly difficult. It's actually a good break here in the middle of this section. And then we'll get into the compositions and learn how to do those in the domains with that. All right, so let's take f of x is equal to 5x minus 3, and g of x is equal to negative 2x plus 7, something like that. Just simple functions to deal with. And they want us to find f plus g of 2. F plus g of 2. Okay. What that means is you find f of 2 and g of 2. And then you add them together. So what we're really doing is taking 2 as the x value and plugging it in to the functions, both of them, and then adding the answers up. So we're adding y values together. That's what we're doing here. So f of 2, we're plugging in 2 in for x. It's like that. 5 times 2 minus 3. 7. Okay. Then when I go find g of 2, negative 2 times 2 plus 7. So that'd be negative 4 plus 7 is 3. So then I take those answers. Those are the ones I want. F of 2 is 7. G of 2 is 3. 7 plus 3. So F plus G of 2 is equal to 10. So you're working it out for each individual problem and then doing the operation with those. Okay. Same idea if I ask you to do F times G of 2. Let's take F of 2 and multiply it times G of 2. We already know what those are. We know F of 2 is 7. And we know G of 2 is 3. 7 times 3 would be 21. So F times G of 2 is equal to 21. So operations for particular x value numbers, function values, is you're really doing the math with the multiplication, or here multiplication. We're multiplying the y values together. Okay. Same thing if you did subtraction or division. You're not really worried about domain and all that other stuff here. You're just working this out. You're just taking numbers, working out the operation out of that. So it's not too bad. All right, let's talk about composition. And this is, maybe the tougher thing we do today. Just because the domains are are sometimes tricky on this. All right, so function composition. Function composition has a unique way of writing the notation. F, and then it's a circle, not the letter O. So it's F composed with G of X. That's how you read that. So it's red, f composed with g of x. That's how that's red. Okay. The math f composed with g of x means take the g of x function and put it into x in the f of x function. Whatever equation or function is listed second goes into the first. Okay. If I said g composed with f, the other direction, that would be take f of x and put it into g of x. We'll see this as we'll do some problems where we do this and then talk about the domains and all that stuff as well. Okay. So take the second function, put it into the first function. So start at the back and work your way forward. It's kind of how you want to think about composition. Start at the end and work your way into right to left here with composition, which it seems counterintuitive because that's what you've always done left to right. So, all right, let's take a couple of functions. F of x equal to 2x minus 1, g of x equal to 4 over x. Let's first talk about the domain of each of these before we get into doing a composition. F of x, what's its domain? Does it have any restrictions? Are there any red flags in 2x minus 1? No. So its domain has to be from negative infinity to positive infinity. All right. G of x, does it have any red flags? Yeah, it's got that x minus 1 in the bottom. So I've got to take care of that. So x, add 1 to each side. X can't be 1. So the domain for it would be from negative infinity up to 1, and then from 1 to infinity. Or, the set notation, x can't be 1. That's maybe it makes it a little easier to think about, maybe. Now, when we do composition, we've got to deal with plugging one thing into the other. So whatever's listed second is acting like the x. Okay? It's acting like x. All right, that's what you want to think about when you're talking about composition. All right, so if I did example number, I'm on JK. All right, so example K says take F composed with G of X. Okay. So what that means is take G of X and put it into X in the F of X function. So that's going to be 2. And instead of putting an X there, I'm going to put a set of parentheses and put 4 over X minus 1. And then there's a minus 1 on the outside. Okay. So I've taken the G of X function and I've picked it up and I've put it in the place of X in the F of X function. Okay. Now, I can simplify that a little bit because I can multiply 2 times 4 on the top because this is really 2 over 1 times that. So that'd be 8 over X minus 1 minus 1. That's all I really can do to this. F composed with G of X. That's what that function composition, that's the composite function is what it's called. Called a composite function. Now, with that, the domain the restriction from the G of X function is now part of the F of X function, right? Because that G of X function went inside the F of X function. So that domain from the G of X function is going to carry over and now be the domain of our composite function because we had a restriction there, right? X can't be negative or positive 1 or from negative infinity to 1 union 1 to infinity. Both of those. So the second function had a restriction. So we had to know, okay, well, the first one didn't have any restrictions, but the second one did. So the second one's restrictions came with us. All right. Let's do that composite function the other direction. Let's do g composed with f of x. Again, that means take f of x and put it into g of x. Okay. Remember, g of x was 4 over x minus 1. F of x was 2x minus 1. All right? So there are no restrictions in f of x, but there are restrictions in g of x. So this is where it gets a little bit more complicated, because when I plug that in, I'm going to have 4 over 2x minus 1 minus 1. Okay. So I've got this extra stuff that I could simplify in the denominator. Now, what I want you to kind of try not to do is take this and look at it before you simplify. Okay? What was the restriction on g of x? That x could not be what number? 1. What we need to know is, when does f of x equal 1? So when is f of x equal to 1? So we set 2x minus 1 equal to 1 and solve that problem. Divide by 2. Hey, it turns out to be 1. It's not always going to be the same number, but it happens to be on this one. So we know that already we could tell you that the domain is going to be all x as long as x not equal to 1. That's coming from there. Okay. I can simplify this, because 2x minus 1 would be 2x minus 2, right? And there's my composite function. The reason I say don't simplify before you start thinking about the domain is because sometimes the simplifying might be the hardest part, and they might not even be asking you for the composite function. Now, a lot of the questions that you'll see on the final and on Canvas quizzes and even in this textbook are not asking you for the composite function. They're just asking you for the domain of the composite function. So you don't have to do all the math that it takes in algebra that it takes to do the composite function. You just got to be able to visualize what the domain is going to be of that. Let's look at another set of functions and see some of the nuances of finding the domains out of that. So let's take a different f of x and say it's the square root of x. And then g of x is 4x plus 2, something like that. Let's find the composite functions and then the domains on those, okay? So f composed with g of x. We'll start with something easy like that. So that means you take g of x and plug it into f of x. So that's going to be square root, and then we put 4x plus 2. Here's what's happening. This is, if we can take this concept out of this, what's the domain of this one? All x's as long as x is greater than or equal to 0, because we can't take the square root of a negative number. This one is all real numbers, and it's shorter to write it like that. Those aren't our final answers, so that's why I'm kind of just trying to use the short method on those. Okay. Now, here's what the way you need to think about composite function domains, even when they get a little bit more complicated, is look at this and say, okay, if I'm going into the f of x function, I need to know when is the g of x function going to meet that restriction? When is g of x greater than or equal to 0? That's what I need to know for the domain. Look at the composite function. The composite function is 4x plus 2 underneath the square root. That's exactly how you would find when is g of x greater than or equal to 0. When the functions get a little bit more complicated, you could end up having trouble getting what's underneath the square root. If there's more stuff going on, if there's a fraction under there, it could cause issues if you've got to simplify it first to solve it. Here, if you just think about it in simpler terms, when does the one I'm plugging in meet the restriction of the one I'm plugging into? Okay. When does the one I'm plugging in meet the restriction of the one I'm plugging into? That's what you got to answer. So we're going to answer that by subtracting 2 and then dividing by 4. And that's going to be x is greater than or equal to negative 1/2. So the domain of this thing, so there's our function, our composite function, with a domain of x that's at x is greater than or equal to negative 1/2. If we did that in interval notation, negative 1/2 with a bracket up to infinity. Notice that that's nowhere in the original domains of the original functions. So you're composite functions can all a lot of times create something new. All right. Let's look at function value with composition functions. Okay, so let's take these same two functions. F of x is the square root of x, and g of x is equal to 4x plus 2. And just do function value with composition. We're not worried about domains here. We're just doing function value. So let's say we had f composed with g, and we want to do of three. That's a good one, I guess. Doesn't really matter. Now, f composed with g of 3. That means we're going to take g of 3, we're going to get its answer, and we're going to put it inside of f. That's what the composite function notation says that we're going to do. Okay, so that means we need to find out what's g of 3. 4 times 3 plus 2. 12 plus 2 is 14. Okay, so g of 3 is 14. So that means I'm going to take 14 and put it into f and try to simplify it if at all possible. This one doesn't simplify. The square root of 14, we could try to break down 14, 2 and 7, but there's not a pair of integers there. So let's go to square root of 14. That's the final answer of that. But where would you get the 14 from? You've got to go into the second function first and get that. Let's take a couple of functions like this. F of x is equal to 2x squared minus 3x plus 5, and g of x is equal to 7x minus 2. Something like that. I know it's going to give me some numbers. Let's say we had f composed with g of negative 1. Where does negative 1 go? Into which function? Goes into the g of x function. This one into that one. So we find g of negative 1. 7 times negative 1 minus 2. Should be negative 7 minus 2, which is negative 9. Okay. So then I'm going to take negative 9, and that's going to go into F. So 2 times negative 9 squared minus 3 times negative 9 plus 5. It's 2 times 81 plus 27 plus 5. So that'd be 162 plus 32 be 194. So F composed with G of negative 1 is 194. All in the order that you put stuff in there. So if in it same time, if I took those same two functions and did the composition backwards, and let's say we did G composed with F of negative 1. In that order, which one does negative 1 go into? Goes into F. So we're going to find F of negative 1 and then put that answer into G. So F of negative 1. 2 times negative 1 squared minus 3 times negative 1 plus 5. That'd be 1 times 2 is 2 plus 3 plus 5 be 10. So I need to take 10 and plug it into G of X. 7 times 10 minus 2. 70 minus 2 is 68 as a final answer. So much different answer going in the other direction. So you've got to make sure when you're doing composition, you're going backwards, right to left. Is how the composition stuff goes. Okay, so composite functions. All right, so let's take a short break.